Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. When you look at a painting by Johannes Vermeer, say, the luminous blue headscarf in Girl with a Pearl Earring, you are witnessing not just art, but a ticking chemical clock. The deep, rich blues that defined the Dutch Golden Age weren't always the rare and expensive lapis lazuli. Many artists, including Vermeer, relied on a more affordable, if volatile, alternative, smalt. Smalt is, simply put, ground cobalt glass. It's created by heating cobalt ore with potassium carbonate and silica, resulting in deep blue chunks that are then crushed into a fine powder. For centuries, smalt was the workhorse blue pigment. But it held a curse, a hidden, molecular weakness that slowly renders the color pale, gray, and eventually, transparent. The decay of smalt is a slow-motion catastrophe. Researchers analyzing these 17th century masterpieces noticed that the pigment isn't merely fading, it is structurally collapsing. The villain in this story is the potassium content, specifically the potassium ions, or K+. These ions are loosely held within the silica cobalt glass lattice. When exposed to humidity, even the minor fluctuations in moisture within a museum, water molecules attack the pigment. The potassium ions leach out, replaced by hydrogen ions from the water in a process called ion exchange. This chemical substitution puts immense stress on the entire crystalline structure. Over decades, this microscopic tension causes the glass particles to fracture into sub-micron fragments, completely scattering light and destroying the pigment's ability to hold its color. It's a spectacular example of catastrophic structural failure at the molecular level. Now, here is where the story takes a truly unexpected turn. What does the slow, chemical decay of a 17th century painting have to do with weather prediction? The answer lies in the universal physics of failure, turbulence, and boundary layer collapse. In atmospheric science, one of the toughest challenges is predicting turbulence and severe weather genesis. This often happens along shear layers, boundaries between two masses of air moving at significantly different speeds or directions. For instance, the interface of the jet stream with surrounding tropospheric air. This velocity differential creates immense stress, known as atmospheric shear. When the difference in speed, or the shear, becomes too great, the boundary layer collapses, not gently, but violently. The collapse is often visualized by the formation of characteristic swirling patterns, the famed Kelvin-Helmholtz instability. These large, rolling eddies are crucial because they mix the atmosphere, dragging fast air down and slow air up. And they are frequently precursors to the rapid intensification of storms and clear air turbulence that plagues air travel. Surprisingly, the mechanism by which the smalt crystal fails mirrors the dynamic collapse of an atmospheric shear layer. In the paint, the driving force is a chemical potential difference, the potassium ions desperately wanting to escape the glass matrix. In the sky, the driving force is a velocity potential difference, the rapid movement difference between air masses. Both systems deal with escalating internal stress by collapsing their boundaries. The smalt pigment breaks its lattice boundary to minimize chemical energy, shattering into dust. The atmosphere breaks its velocity boundary, forming Kelvin-Helmholtz waves to minimize kinetic energy. They are essentially two forms of the same chaotic, boundary-dissolving instability, one frozen in time on a canvas, the other playing out in milliseconds in the sky. Art conservationists use advanced non-invasive techniques, like synchrotron radiation, to map the structural degradation of these priceless pigments. They can effectively study the long-term, slow-motion failure of a structurally stressed material. Climate scientists and fluid dynamicists are now recognizing the value of these conservation studies. The decay rates and patterns observed in smalt offer a macro-scale, time-slowed analogue of processes like turbulent mixing and boundary collapse that happen too quickly and chaotically in the atmosphere to model precisely. By analyzing the crystal curse, researchers gained tangible, physical data on how stressed systems move from stability to chaos, offering new mathematical parameters to refine predictive models for atmospheric turbulence and severe weather. The next time you see a masterpiece, remember that its fragile beauty might be concealing data about the turbulent world outside. The hidden chemistry in Vermeer's blue is whispering secrets, not just about art history, but about the very forces that shape our weather. For more incredible facts like this, don't forget to subscribe and turn on notifications.